Hello there, students. In this video, we're going to apply the Biot-Savart equation to find the B field at a point on the bisecting axis of a finite straight wire, somewhere along this dotted line. We'll pick an arbitrary point on this dotted axis. We start with the differential form of the Biot-Savart equation. If we take the current to be flowing to the right, then we can pick an arbitrary piece of the wire to represent our infinitesimal length dl, which will also be directed to the right. From this vector dl to the point of interest on the vertical axis, we have vector r. The distance from the midpoint of the current wire to the point of interest is a distance capital R. If we take the direction along the wire to be the x-axis, and the direction along the vertical to be the y-axis, then the distance from the midpoint to vector dl is a length x. We are also going to label a lot of angles here. Starting with the angle going counterclockwise from vector dl to vector r, we'll label this with a phi. The angle that vector r makes with the x-axis we'll label with a psi. And then lastly, the angle that the vertical axis makes with vector r we'll label with trusty old theta. We need to take a quick look at this geometry to make some observations. Namely, let's look at the relationship between this right triangle we've made and the angles we've labeled. There is a relationship between psi and phi in that psi is equal to the angle pi minus phi. We can also see that the cosine of theta equals capital R over r. And the sine of psi is also equal to capital R over r. Substituting psi equals pi minus phi, we can see that this equality holds. If we now take a look at a unit circle, we can understand the sine of an angle to be measuring the y-coordinate, or the height or vertical length of the green bar here. If we put angle pi minus phi on the unit circle, and look at the sine of that, we see that it is the exact same value, as long as we put a constraint that phi is less than pi. What this means is that as long as the constraint holds, the sine of phi is equal to the sine of pi minus phi, which we've already shown is equal to the cosine of theta. That's the most important result from all of this. The sine of phi is equal to the cosine of theta, which is equal to capital R over r. Since we have the wire along a certain axis, we can be more concrete about what this vector dl means. It's just an infinitesimal length dx in the x direction, x hat. We can also use the Pythagorean theorem to see that r squared is equal to capital R squared plus x squared. We can quickly update our equation with these new expressions. I'm also changing vector r into a unit vector, meaning we lose a power from r cubed, making it r squared in the denominator, which is then substituted away into capital R squared plus x squared. Now, following a right-hand rule or evaluating the cross product, we see that the B field at our point of interest will only be in the positive z direction. So with the direction under control, let's take the magnitude of the differential Biot-Savart equation. The magnitude of the cross product yields the magnitude of x hat times the magnitude of r hat times the sine of the angle between them, which is what we labeled as phi. Don't forget that the magnitude of a unit vector is equal to 1. We've already proven that the sine of phi is equal to the cosine of theta, which is equal to capital R divided by r, where we can substitute in what we found via the Pythagorean theorem for little r. Putting this all together, all we need to do now to get the full B field is integrate along the length of the wire, where capital L is the length of the wire. Since the integral is symmetric, meaning we are going to be integrating from the left side of the wire, which is a distance x equals negative L over 2, to the middle where x equals 0, and then from the middle to the right side where x equals L over 2, and all of these components add to the B field, we can instead integrate half of this wire and multiply our resulting B field by 2. We can look up this form of integral on an integration table to get this result, where they use the letter a as a constant. This is what we are calling capital R. Evaluating the integration limits, we find, and then simplifying by pulling a factor of L over 2 out of the square root, we get. So, if you know the length of the wire L and the distance from the midpoint capital R, you have the magnitude of the B field. A common extension of this problem is the infinite straight wire. If we want a solution to the infinite wire problem, all we need to do is take what we already have and let the length L go to infinity. If we do that, and take a closer look at the fraction in the square root, we see that as L goes to infinity, we're dividing by infinity, which means this term, this fraction, approaches 0. Then, all we're left with in this equation is... This result is a lot easier to obtain using Ampere's law, but that's okay. This is just another method to get the same result. Thanks for watching and learning about physics. If you have any questions or want to see a specific topic, leave a comment below or head over to my Facebook page in the video description.